Hey, John, I think we'll get started here.
Sounds good.
Yep, so let me talk to the participants here for a second. So I just wanted to say hello to everyone, and thanks for coming. Thanks for your interest in JMag and also GT Suite. So my name is Brian Kowalczyk from PowerSys, and I want to welcome you to this session regarding a multidisciplinary approach to integrated motor modeling using GT Suite and JMag. So our speaker today will be Jonathan Zeman of Gamma Technologies. And Jonathan is the application team lead for vehicle and electrification. He has been with Gamma Technologies for 12 years, focusing on vehicle systems modeling, including fuel economy and performance, energy management, drivability, and vehicle NVH. So prior to joining Gamma Technologies, John obtained his master's in mechanical engineering from the University of Iowa in 2009. So I now would like to welcome John to share his presentation. So you can take it away, John.
Perfect. Thanks, Brian, for the introduction, and hello, everyone, and thanks to JSOL as well as PowerSys for giving Gamma and myself the opportunity to present at this year's user conference. It's my pleasure to be speaking to you today about a multidisciplinary approach to integrated motor modeling using GT Suite and JMag. So for my presentation today, I'll cover several topics. First, kind of an introduction to Gamma Technologies and some highlights into our product, which is GT Suite. Next, I'll examine the need for integrated multi-physics simulation, which will bring me into the collaboration that GT and JSOL have been building together for a couple of years now, and that will kind of set the stage for discussing some of the solutions that we've been bringing for thermal integrated NVH and thermal management. So Gamma Technologies is a software development company based out of Chicago in the US. We were founded in '94 with the goal of providing system-level multi-physics engineering software for primarily the automotive industry. And since our founding, we've expanded to offices in Europe, India, and as well as the Asia Pacific region, represented there by IDAJ. And we have a singular focus, which is development and support of GT Suite software around the globe. So you might be asking yourselves, what is GT Suite? This is our product. It's a multi-physics engineering software which contains various libraries, for instance, electrical, to build any kind of electrical circuit, from map-based kind of data-driven models to more physics-based models. We also have a lot of capabilities in the thermal area to build things like thermal networks and finite element structures, so lumped models, to more detailed and discretized models. We also have pretty extensive libraries for fluid flow. For instance, here we show a priming simulation of an oil circuit, but it can also be used for electrification. For instance, here we're looking at kind of the stator cooling jackets of an electric machine. And then also in the mechanical domain. So we have models for driveline dynamics, vehicle dynamics, as well as higher frequencies for NVH. And lastly, really one of the core competencies of GT Suites is the full system or system integration. So bringing those individual subsystems together for a complete vehicle model. Now, working with many customers in different market segments and also geographical locations, we've really seen one common theme, which is the need for closer collaboration between different departments. And we've seen that as electrification brings new powertrain challenges, together with pressures to decrease development times, increase powertrain efficiency, and decrease cost, there's really a need for increased collaboration. But we've seen that many traditional workflows and processes are decoupled, kind of what you see on the screen here, where, for instance, motor teams work largely in isolation from other teams like control, thermal, and NVH, who need that motor as not just a boundary condition, but an integral part of their system. And so, while this has historically led to, I would say, satisfactory results, we see a need for an increased level of collaboration between the different departments. And so that's what led us to our collaboration with JSOL. We've been trying to develop a more streamlined approach suitable for every stage of the development process, kind of starting with the system level vehicle architecture, but then moving down the V toward the right side for more of the topics that we're going to be talking about today, which have to do with some of the more detailed motor integration and control, as well as the full vehicle validation. And so for this, we're going to be relying on some detailed 2D and 3D electromagnetic analysis. That's not something that GT historically has done internally, which is why we've partnered with JSOL. And you'll see a little bit about how we use this partnership with JSOL to accomplish some of these more advanced tasks. So speaking in the higher frequency domain here, which is going to be the main part of my presentation, we typically look at different requirements, which can be grouped kind of based on the frequency range. So typically, vibration problems are lower frequency and can be solved using a 1D multi-body dynamics approach. And these manifest themselves as vehicle phenomena like shuffle, judder, and clunk, which you kind of see on the lower left-hand side. But other phenomena, higher frequency phenomena, typically will require a fully 3D or coupled 1D, 3D approach to solve things like rattle, moan, and imbalance. And then eventually, we reach the higher frequencies, which are typically noise, radiated noise. And so when we look at holistically at these next generation vehicle and powertrain architectures, we can identify that the noise footprint of the vehicle is different compared to an internal combustion engine powered vehicle, and especially at low speeds where now the wind and road noise are low, so the powertrain noise kind of dominates. So looking in more detail at this problem, we can see that in the case of the combustion engine, many NVH factors were masked by the engine noise. And now that noise is gone in the case of an electric vehicle, the occupants of this vehicle will be subject to this powertrain noise. And so I'm going to focus mostly on the e-motor and gearbox dynamics here, and kind of looking at this this graph in the upper right, we can see that the noise profile of the BEVs in blue is typically lower than the internal combustion engine powered vehicle, except at some key operating points. And we've seen that because of this different noise profile, regulatory bodies in all the major regions are kind of taking notice and issuing new regulations, which makes acoustic CAE in this particular area more important. So the process to determine these new noise sources is pretty complex and really requires a full suite of multi-physics simulation capabilities. And starting with the power control unit, the inverter, will provide electrical excitation to the motor. And of course, this excitation itself may cause a noise in the wiring. But really, depending on the motor construction and the quality of the electrical waveforms, the motor will be the main source of vibration here. And these forces produced in the stator will create stator vibration and therefore noise. So what we do is we take the forces and we use these as boundary conditions for our full powertrain analysis via a multi-body dynamic characterization of the powertrain machinery. And of course, we have some submodels for things like bearings and gears. Then what we do is we complete a full FE analysis on the housing structure, reacting from the loads from the magnetostatic analysis and the vibration from the powertrain. And then we perform an aeroacoustic analysis to resolve the radiated noise field of the powertrain. So the acoustic analysis is rather new to GT. The other elements have been in the GT Suite software for some time now. So to enable this process, we take advantage of the electromagnetic force output for NVH from JMag Designer, and this allows GT to import the local forces on the stator for excitation. These electromagnetic force files get imported in CSV file format, which GT reads in directly, and these give the constituent X and Y direction forces as a function of the rotor angle at each stator tooth, which then are applied as boundary conditions to the stator mesh, and that stator mesh is merged with the gearbox housing to create a complete powertrain mesh. And so these excitation forces from the electromagnetic model act as boundary conditions within the larger model. As I mentioned, that's going to include the gearbox housing, gear train, shafts, bearings. And so really what we have here is a one-way coupled simulation such that the forces from JMag will affect misalignment of the gears and housing deflections, which are then all solved in GT in the time domain. And of course, these housing deflections create surface vibrations, which excite the surrounding air and create noise. Future step, which we're looking into, will include looking at eccentricity of the electromagnetic solution so that we can get, even though it's really a one-way analysis, we'll have those two-way interactions. So we've discussed that the noise comes from the surface vibrations of the E-axle, but we also need to look into what else will contribute to surface vibrations of the housing. And so looking at the gears, there are many elements that can cause these higher frequency harmonics, which multiply and kind of distribute the engine or the motor torque to the vehicle wheels. Some of these include dynamic phenomenon like tip tooth contact, as well as local deformation, misalignment, as well as gear shuttling forces and friction. And these can all be contributors to some higher order harmonics. But there are also things like machining and manufacturing imperfections that can also come into play here. Of course, the gears don't operate in isolation, but rather connect to the housing structure through the bearings, which requires a model. And so within GT Suite, we provide bearing models based on ISO standards for various bearing types. And these, of course, transmit the loads within the gearbox to the housing structure. So to begin to study the vibration of the E-axle housing, we start by extracting the loads on the E-axle housing from the previous coupled multi-body dynamics and FE time domain analysis. And we take an FFT of these forces and apply them at the boundary locations, for instance, at the bearing locations or the stator teeth, and we can make a linearized force to frequency analysis of the gearbox structure. And this allows us to resolve the operating deflection shapes at a particular frequency and allows us to further investigate the frequency response at the nodal locations of interest in the form of Campbell diagrams. Now, once these operating deflection shapes have been resolved across the frequency range of interest, it's possible to perform the acoustic analysis. So there are various methods to perform this type of analysis. One of these is the monopole solution. And by placing a monopole at every node on the mesh, which you can see kind of on the figure on the right, we can track surface vibrations on the body, which generate sound pressure levels for each monopole at the microphone location. These are then summed together at the microphone location so that the noise profile can be captured. Of course, for runtime purposes, we omit occluded monopoles, which are basically behind the body. And so far, comparing this technique against more computationally expensive techniques has yielded some pretty good results. But we do have another possibility, which is to use the wave-based technique. And here I'm showing our new solution for acoustic performance using the wave-based technique. The advantage here is that it's accurate and allows for faster results than some more conventional finite element and boundary element techniques. And on the right side here, you can see some of those operating deflection shapes at different frequencies. So far, I've shown GT and JMAG coupled solutions which allow engineers to model an e-axle assembly, starting with the motor and tracking performance all the way to the system acoustic signature. Clearly, this analysis is very powerful and detailed, but it doesn't represent the only solutions that GT and JSOL have tackled for NVH challenges. As many of you are likely familiar, there's another avenue besides electromagnetic NVH force export that can be used in system level models, and that's via JMAG-RT. So with JMAG-RT, it's possible to export the RTT file, which contains those rotor angle dependent flux linkage maps. And this allows the GT system level model to utilize JMAG-RT to predict e-motor transient torque. We can apply various motor drive technologies such as MTPA, field weakening, SVPWM to track the motor response at the complete driveline and vehicle level. So in such an integrated model, we can evaluate, for instance, torsional NVH responses due to engine, motor, damper interactions. And what this allows for is really earlier, more upfront NVH analysis, which previously hasn't been possible. Now, a couple kind of concluding slides here beyond mechanics and thinking about next steps and where GT and JSOL can continue to work together to help solve your challenges is in the thermal domain. So similarly to how JMAG Designer has the force export for NVH, we're also working together with JSOL to take their export for thermal quantities. So basically the heat generation rates coming from JMAG Designer in the form of the CSV file, as I mentioned before, and also the Nastran mesh, which will import into a GT representation of the electric motor. So together with the JMAG boundary conditions and the thermal mesh, we can basically incorporate that into a GT suite model, which you see on the lower left corner here, which can be a mixed 1D and 3D model, including fluid flow to take into account some of the transient effects of the powertrain cooling. And so what we're able to do is really start with a completely geometric and parametric based model. And as the design is refined, work at different levels of fidelity to be able to look at complete motor cooling system combined with the electromagnetics to really bring a predictive solution for making upfront decisions regarding motor design and control, for instance, thermal derating strategies. So hopefully I've shown that together GT and JSOL are working together to reduce obstacles to collaboration. And so really we're working here to create more streamlined workflows, which will make things more efficient for you as the end users. So with that, I want to thank you for your attention. Also, again, thank JSOL as well as PowerSys for the opportunity to present our joint work. And I know we went through that a little bit quickly, so we hopefully have some time for some questions.
Yeah, Jonathan, thank you very much. Big thanks for your presentation and your time and resource. I mean, great presentation on the JMAG and GT integration. Thank you. So yeah, we've got time for Q&A. So we can start that now. And if anyone has questions, you can enter those in the Q&A panel in the Whova application. So John's available for questions. Thank you. So I have one question here, John.
Sure.
So how is force mapping done from JMAG to GT? You might have touched on that, but could you possibly review that again?
Yeah. Let me just kind of go back to the slide here. Okay. So I'll admit that it's actually one of my team members here who's the kind of the absolute expert here. But essentially we're getting a CSV file from this force export for NVH coming from JMAG Designer, and that will have the X and Y components of the force and the XY position of basically that where the force gets applied on that stator tooth. So we basically took advantage of some functionality that that JMAG Designer already had, and with JSOL's help, we're basically able to kind of reconstruct that force export on the mesh which exists in the GT Suite environment.
Okay. Thank you.
Yeah, I think actually here's here's kind of a snapshot of what those forces look like. So obviously there's there's an angle dependence here, and so we basically read in this this file format and apply it to our as a boundary condition to our mesh.
Okay. Thanks for that answer. So we have a couple minutes left. We can handle another question from the participants. Pose it on your Q&A panel in Whova. Thank you. So we have another question here, Jonathan.
Okay, perfect.
So, ready? So how does GT calculate the temperature change with JMAG model? Is this based on FEA or equivalent circuit?
Okay, that's a great question. So GT, let's see if I can find. So GT has a few different options here for thermal modeling. We don't use like an equivalent circuit analogy, everything is physics based, but you're going to get a couple different levels of fidelity. One would be kind of a lumped, so we'll call it a thermal mass approach, where you can discretize, for instance, the stator into, let's say axially five thermal masses, and you'll get some temperature gradient within that thermal mass, but by and large, that thermal mass is kind of one unit. But then we can see on the right, an alternative approach would be to use more of a finite element formulation, which computationally is a little bit more expensive, but is going to give you that higher resolution. And so those are kind of the two high level approaches, and they're not even necessarily mutually exclusive. So it's possible to zoom in and mesh, for instance, the end windings, for instance, if that was a critical temperature area for you. So hopefully that answers the question from the thermal standpoint. I should also mention that most of these problems are coupled thermal fluids. So we have a very strong 1D fluid flow capability to model the heat transfer coming out of that, either that thermal mass or the meshed part into some kind of cooling system.
John, thanks a lot for that answer.
Sure.
So, well, I'll tell you what, I think we're at the closing time for the session.
Okay.
It's right about 3:50 now. So, John, thanks for the presentation. Thanks for the answers.
Yeah.
Appreciate your effort there. So this session's over, and I want to tell the participants you can switch to the next session in Whova, and the topic is multi-physics modeling of electric motor cooling strategies. So if you have any technical issues, you could try refreshing your screens. So feel free to join that next session. It's coming up here in just a minute. So everyone, thanks for joining, and thanks to Jonathan, and we'll end the session now.
Thanks, everyone.
Jonathan, we'll see you later. Take care.
Thank you. Bye-bye.
Okay, bye-bye.